Hello everyone, I'm Michael Munex from the University of Queensland in Brisbane, Australia. I will present our recent results with Nick Fontaine and his colleagues from Nokia Bell Labs in the US on how to generate arbitrary spatiotemporal optical fields. To give you a taste on what we will present today, here we can see experimental results that were generated with our apparatus. We can see three different patterns with different spatiotemporal response. An Eiffel Tower as a function of time, a smiley face being delivered at a specific delay, and a spot scanning following a spiral trajectory as a function of time, with two different spirals for the two orthogonal polarization states. Let's see now how we did it. So I will first give a brief introduction on optical beam shaping and why the generation of arbitrary optical fields has never been done before, including a full control of all of the light's properties, both transverse and longitudinal. I will then detail our solution to control the properties of light simultaneously with a new device, which enables to generate arbitrary optical fields. I will then present the experimental setup of the device and its performance for generating arbitrary optical fields, leading to the first generation of time-reverse optical waves before concluding my talk. So first, let's talk about optical beam shaping. So optical beam shaping has been discussed since the 20th century with the emergence of pulse shapers by means of spatial light modulator located in the Fourier plane of a dispersive optical element. The optical beam shaping research field has since grown exponentially, with spatial light modulators being more affordable and with the development of new research fields driven by demand. Many recent reviews outline the different spatial light modulator technologies and recent applications in fields that require structured light. I will not discuss at all the applications that resulted from the ability to shape at will the optical field, but I will show some recent nice examples that will also motivate our recent work. So for instance, adaptive optics is a form of beam shaping that requires deformable mirror, usually between 10 and 1000, and a wavefront sensor, such as a Shack-Hartmann. A feedback loop between the wavefront sensor and the deformable mirrors enables to compensate for the aberrated wavefront by adjusting the position, the tilt, and the local curvature in the mirror plane to obtain a flat wavefront after the light bounces on the mirror. The ability to remove such aberrations found two major applications in astronomy, where double stars could be discovered, as well as in microscopy, where aberration used to limit the delivery of light in biological tissues, not at big depth. Other applications of structured light enhance its interaction with matter or to encode information. Amongst the big reservoir of light-matter interactions improved with spatial light modulators, a typical example is optical tweezers and trapping, where the structured light enables to transfer angular momentum to trapped particles. In optical communications, spatial and wavelength division multiplexing enable to increase optical fiber capacity to carry more information with different signals traveling in orthogonal fiber modes at different wavelengths through the same fiber core. So this is enabled by launching structured light through the fiber. Finally, another range of application is the delivery of light through complex scattering materials. Most of the power of an incoming plane wave would be backscattered, and the power that transmits through the material suffers from complex interference between all the modes of the system and leads to what we call a speckle pattern. Recent advances in wavefront shaping by means of spatial light modulators enable to focus light through complex materials such as white paint, biological tissues, or multimode optical fibers. The partial control of the light's degrees of freedom also enabled imaging through such materials, an advance which was beyond imagination a few decades ago. Okay, so after this brief discussion on why beam shaping is important, let's discuss more of its details, especially on how to control the light's degrees of freedom. So now let's explore how to control the light's degrees of freedom by means of spatial light modulators. So the degrees of freedom that we have to control are the following. So we've got the two spatial dimensions, which is the transverse dimension of the field, and 1D spectral or temporal dimension, which is the longitudinal component of the field. We also have to control polarization, which is a subpart of the transverse field. So now here is the challenge. We have a spatial light modulator, and this is a 2D display. So how to control all these degrees of freedom? So this dimension mismatch, because we have a 2-dimension to control on the SLM with the 3-dimension to control, is what blocked the advance of controlling all the degrees of freedom simultaneously. So today I won't discuss how to control a pure CW beam, as you can then use the full 2D display to control both the amplitude and the phase of the optical field, as well as polarization. So the full transverse field can be controlled. But now I'm going to discuss how to control both the spatial and the spectral degrees of freedom of broadband light. So recent works have demonstrated partial control of light in scattering media, where the medium couples the spatial and temporal degrees of freedom. Therefore, temporal properties of the field can be controlled with space-only shaping on a spatial light modulator. So spatiotemporal focusing was demonstrated, which implies the ability to deliver light at a given position and at a given time. However, the background spatiotemporal speckle around the focus cannot be controlled. Similarly, a temporal-only control of the spatiotemporal speckle field was demonstrated. So all the speckle grains are focused at a given time, but at the expense of what the spatial speckle looks like itself. So there is always a price to pay to achieve this control, as with the 2-dimension of the spatial light modulator, we do not control the entire spatiotemporal scattered field. We only have a partial control due to this dimension mismatch. Indeed, the hologram that we display on the spatial light modulator is the superposition of 2D phase patterns for each wavelength. So if we think about the targeted field and we backpropagate this field towards the SLM plane, the different wavelength components will overlap on the SLM surface, meaning that these different spectral degrees of freedom are sharing the same spatial degrees of freedom on the spatial light modulator, the same SLM pixels, and thus cannot be controlled independently. So although such superposition of holograms provides enough degrees of freedom to create a spatiotemporal focus, it doesn't really show the way towards a full field control. So to avoid this superposition of spectral holograms on the same surface of the SLM, spectral pulse shaping provides a solution. So a femtosecond pulse is dispersed with a grating, and the spectral components are imaged along one dimension of the SLM, so the x-axis here. And then the y-axis of the SLM can then be used for spatial steering. So the different spectral components can be steered to different spatial positions. So such spectral pulse shaper was used and applied for spatiotemporal focusing. So firstly, the speckle field for each spectral component along one spatial dimension is measured using a 2-dimensional spectrometer after propagation through the scattering sample, which is here a layer of white paint. In a second step, the speckle is phase conjugated for each wavelength of the incident pulse, and the corresponding phase mask is applied onto the spatial light modulator within the pulse shaper to create a spatiotemporal focus. However, we can only control one spatial dimension rather than the two required spatial dimensions for full field control. A special breed of pulse shaper was also developed in the optical communication community, the wavelength selective switch, since the early 2000s. The principle is very close to a pulse shaper. An input pulse coming from a single mode fiber from a fiber array is dispersed onto a grating, and then a SLM here is located in the Fourier plane of the grating. The beam is then recombined through the same grating, and light can be steered into the different ports of the fiber array independently for the different wavelengths of the input broadband beam, since all the wavelengths are here split across the x-axis. So such a method enables specific correlation between the spatial angle and wavelengths, as a tilt is usually displayed on the SLM across the vertical axis, which enables different beam steering for different wavelengths. So for instance, here in this mask, the two polarization states can be split on the left and the right side, and all the wavelengths, which are split across the x-axis, are steered here with different angles to the different ports of the fiber array. So in this mask, also some calibration are added to map the wavelengths per SLM pixels, So therefore, each wavelength is not rigorously a straight vertical line on the SLM. So such method enables wavelength division multiplexing. However, it only enables, again, a two-dimension control of the light beam, one dimension spatial and one dimension spectral. So in summary, the recent works enable to control only two of the three required dimensions to get a full field control. So I will present now our trick to fully control the three dimensions of the field using only two dimensions of the SLM. It relies on the use of multiplane light conversion system. So the multiplane light conversion, abbreviated MPLC, was recently developed to perform unitary transformation. So the MPLC technology has been out for the past decade, mostly coming from the need of unitary transformation carried out here by using phase mask. In our case, we will exploit a technology of the MPLC that has been developed between the University of Queensland and Nokia Bell Labs that enables to perform a 1D to 2D spatial transform. So on the left side of the figure here, we can see the input field, which is a 1D linear array of spots. So if we look at the animation from left to right, we can see that each spot gets individually transformed onto a chosen Hermite-Gaussian mode after propagation towards 14 phase mask previously calculated. So in this way, we can excite a two-dimension mode using a single dimension, that is launching the specific 1D spot. So this will be our game changer here. So also, if you look at the same animation from right to left, you can see that each HG mode will back propagate to a unique spot position on the linear array. So this property was also exploited by our research group for efficient mode sorting. So let's dig a bit more into this 1D to 2D transform here. So for instance, steering light to a single port of the array launches the corresponding HG mode. Steering to another spot launches another HG mode. So now launching the good combination of spots, both with accurate relative amplitude and phase control, enables to launch the corresponding superposition of these HG modes and thus creating arbitrary spatial patterns, such as a smiley face here, with only one single spatial dimension. So we now have the ability to control all the degrees of freedom of light. A traditional pulse shaper can control the spectral degrees of freedom as well as one dimension spatial. Using polarization optics, we can also control polarization within the pulse shaper. The output of the pulse shaper is a 1D array of spots with control of the spectrum and polarization for each spot. This 1D array can then be transformed as an image using the MPLC, reshaping the spatial dimension as the full transverse field, leading to a full control of the three critical degrees of freedom. So I will now present our experimental setup that can control all the degrees of freedom of light. So this is how we conceive the experimental setup. So the polarization resolved multipole spectral pulse shaper is integrated into this black rectangle here and is made of an SLM, a grating glued on a prism, polarization optics, and a bunch of lenses that are resizing and doing Fourier transforms. The different spectral components of the input beam are dispersed on the grating and imaged independently along the x-axis of the SLM. The output of the pulse shaper is imaged onto the MPLC here that is made of a gold plate on which the 14 phase masks are printing with lithography and a mirror. So the SLM of the spectral pulse shaper is doing the hard work here with complex holograms steering independently in both the x-axis for spectral shaping and the y-axis for spatial shaping for both polarization states on each side of the SLM. The 1D y-axis of the SLM is then turned onto a 2D spatial beam by means of the MPLC. So here is a real-life picture of the experiment that we set up at Nokia Bell Labs in the US. So this is the polarization resolved spectral pulse shaper here. So the input light comes from this fiber array, and we are only using one port of the array. The other ports are actually used for aligning this pulse shaper. So light goes through the polarization optics, then the grating, and then onto the SLM, which is located in the conjugated plane of the grating. So we will discuss that more thoroughly in the coming slides. Then the light is back reflected on the SLM and goes back to the source with a small angle induced by the SLM to reflect on a mirror just located next to the source, and we will then image the beam to the MPLC. So this is the SLM in the Fourier plane of the grating. So by putting a phase tilt across the y-axis, we will be steering the spot up and down on the grating. So this is how we will be addressing the spatial modes of the system. Different positions along the y-axis correspond with the 1D linear spot array of the MPLC system, which enables later to address the 2D spatial properties of the beam per spectral component. The x-axis is the spectral axis. So steering along the x-axis creates a frequency-dependent linear phase shift. It corresponds to an actual physical different path in the grating, creating a controllable delay. So now, with the control steering of light both in the x and y axis of the SLM, we can control the transverse beam through the spatial control on the y axis for all the wavelength component of the source through the x axis. So then the light exits the polarization resolved pulse shaper and is imaged to the MPLC with the 4F telescope. So we can now see the MPLC with a side view. So we'll see a front view in the next slide. So the MPLC is made of a faceplate printed on a substrate and a parallel mirror. The faceplate contains 14 phase masks regularly spaced that have been calculated to achieve this 1D to 2D spatial transform. Light bounces 14 times and is then injected into the multimode fiber of study, which will add extra spatial mode coupling. This fiber doesn't add much delay as we are using a Telegram grade gradient index fiber. So this is the front view of the MPLC. We can barely see the phase mark on this picture, but ask you to believe me, they are there. Light is injected in the multimode fiber with the green lens attached to the fiber facet. So we now see the beam detection side. So the output facet of the multimode fiber is imaged onto a camera where the light beam is recombined with an off-axis reference beam coming from this collimator here onto a non-polarizing beam splitter. The two polarization states are split with some polarization optics before the beam splitter in this example, which are here. We can then perform off-axis digital holography to reconstruct the beam coming from the output facet of the fiber after traveling through the device. Okay, cool. So now let's actually take a proper look at what we can do with this device. So this is an ultra-fast wavefront shaper. It can generate a sequence of independent wavefronts separated by a bandwidth limited amount of time, that is in our case around 230 femtoseconds, for a duration of 20 picoseconds. So it's about 85 frames displayed at 4.4 terahertz. So now the question is, how do we program the SLM to generate a desired spatiotemporal pattern? So we first characterize the device by measuring its spectrally resolved transfer matrices. So the source we will use is a swept wavelength laser. One path from the source goes through the device itself, and the other becomes the reference for the digital holography. So the spatial light modulator steers to each input spatial mode in each polarization at a time for a total of 90 modes. So we can see here that the spot gets transformed into the corresponding HG mode through the MPLC, which is then coupled into the multimode fiber under test, which is the 5 meter long gradient index fiber that supports 45 modes per polarization state. For each input mode, we sweep the wavelength and reconstruct the corresponding fields with the digital holography. Then we extract the modal decomposition, which correspond to the transfer matrix coefficients for this specific input at this wavelength. And then we iterate through all the input modes to measure the full matrix. Now we can generate arbitrary vector fields in the spectral domain on the output facet of the fiber within the limits of the optical bandwidth and frequency resolution. The target is a set of 90 modal coefficients reconstructing a 2D spatial pattern at a given wavelength. For a target in the temporal domain, we just need to calculate the Fourier transform to get the target in the spectral domain. So how do we do that? We calculate the required input state by backpropagating the desired output state with the transfer matrices for every spectral component. Then the corresponding phase mask is calculated using computational holography algorithm to generate the required amplitude and phase for each coefficient and each wavelength to be launched into the fiber. Once we calculated the mask, we display the mask on the SLM, and then we do a characterization sweep to measure the corresponding obtained optical field. So we record the spatial field for each spectral components, and then we get the Fourier transform along the spectral axis to get the temporal response. So just to insist the temporal measurement that we will do here are done in the spectral domain. So the example illustrated here shows the ticking clock hand from before. In the frequency domain, this is our target, and this is the actual response in the time domain. Cool, so I'm going to show now some experimental results. So firstly, spatio-spectral pattern. So here we generate the English alphabet in the H polarization state and the reverse alphabet in the V polarization. Each pattern has a spectral bandwidth of 50 GHz. The bandwidth of the source is 4 THz, so we can actually repeat in a cycle this alphabet. The overlap integral between the measured patterns and the predicted patterns is about 85% across all the wavelengths, which is a very good value. Now I'm showing a spatiotemporal pattern. So our very accurate control of the spectral phase along the bandwidth of the source provides a temporal resolution of 230 femtoseconds. So in this example, we focus a vertically polarized smiley face at a single delay, 5 picoseconds, within a single time step of 230 femtoseconds. So in the volumetric representation of the data here on the right hand side, the measured signal only appears at the expected delay. Now I'm showing patterns that have multiple delays rather than a single delay. So here it's a 2D raster scan of a circularly polarized focus through the entire field of view. So the spatial position of the spatiotemporal focus changes with delay. The H polarization follows a spiral trajectory, while the V polarization focus follows the out-of-phase spiral trajectory. In this example here, we generate all of the 90 modes separated by 230 femtoseconds within 20 picoseconds, alternating the polarization state on which the mode is imaged onto between each time step. I'm going to repeat this one. So all the modes have been generated now. Finally, we can also create some fancy 3D patterns in the temporal domain that we still don't know how useful that can be, but they look nice, that we can see here in the volumetric plot here. So these patterns are defined through 2D temporal sections. So in this one, we pay a tribute to the Eiffel Tower within 12 picoseconds, where we start with the pillars and then we go through the column of the Eiffel Tower. So the ability to generate arbitrary optical fields could serve heaps of applications within the global space of optics. Note that our device could be used with a multimode fiber as we've done, but can also be used in free space too. To cite a few applications that could be of interest for the structured light community, we have optical manipulation, of course, such as trapping and as we've discussed before. We can also try to help improving the resolution for microscopy or enhancing specific light-matter interaction, such as nanophotonics or plasmonics. Our device could also be useful for the delivery of structured light with very high power for applications such as nonlinear optics, amplification, or optical micro-machining for material processing, such as cutting through glass or polymer in depth, etc. In scattering media, the ability to control the full field through a control of all the modes could also unlock studies that were theoretical dreams so far, such as the potential experimental discovery of open channels, that is some optical path where all the light is transmitted as if there was no scattering process. Our ability to also control fully the field can be used for transferring or delivering light within a scattering material for fundamental purposes or for imaging purposes. Thank you very much for your attention. You can find all the details in this paper and in these two videos, a 5-minute summary and then a technical detail. And the paper also have a very lengthy supplementary material with all the details. Thank you very much for your attention.